Welcome back to the ChemDoctor, and this video is going to focus on the naming of a class of molecules that are called hydrates. And hydrates are ionic compounds that are combined with a number of water molecules. Now, to start the discussion, what we're going to do is focus here on what's called Epsom salt. All right, and maybe you had experience with Epsom salt if your mom put you in the bathtub after having a long day at the soccer practice, and if you're in college, maybe those days were a long time ago. But basically, Epsom salt is magnesium sulfate that is complex to 7 water molecules. And what I want to do to start with is analyze the chemical formulas of these compounds. So you see, the way it works is that the ionic compound itself is, in terms of the formula, is presented on what I call the front end of the formula, and then you notice in the middle there's this big dot. All right, and I'll come back in a second and talk more about what that means. And then we have a number followed by H2O. So the first thing is that you've got to understand the stoichiometry of these things. So I'm going to presume that at this point you've had the discussion about the mole and the basic way that stoichiometry works in chemical formulas. So let's lay this out. If I have 1 mole of this compound, all right, 1 mole of this compound, or even on a simpler level, if I just say, okay, we have 1 particle of this compound, then what you need to know about the relationship between the 1 here, which describes the fact that we have 1 entire particle of this compound, or 1 entire mole of this compound, is that it has a relationship to the 7, which is the following. So for every particle of magnesium sulfate, 7H2O, there are 7 particles of H2O. So for every particle of MgSO4, 7H2O, there are 7 H2Os, and there's 1 MgSO4 within that singular particle. So if we extend this to the idea of the mole, then for every mole of MgSO4, 7H2O, there's 1 mole of MgSO4 in that collection of particles, and there are 7 H2Os per MgSO4. All right. Now, the meaning of the dot. The dot means and. So it means and. All right. And we learn in math that and means plus. So the dot is not a multiplication sign, and that is super important to you guys when you've got to calculate molar mass of these compounds. All right, and for those of you at the college level or in an advanced placement chemistry class, no doubt you're going to be doing some kind of a gravimetric analysis lab where you have to determine the formula of a hydrate. And in those kinds of laboratories, when you go to do these calculations, do not treat the dot like it's a multiplication sign, all right? And in fact, I think to just hammer this home before we actually do the naming, I'm going to go ahead and over here we'll calculate the molar mass of this so you can see how it's done. So maybe we'll kill 2 birds with 1 stone in this video. You'll know, you'll go away at least also knowing how to calculate the molar mass of this. So we'll do a quick back in the napkin thing. All right, the magnesium's worth 24 grams per mole. The sulfur's 32. All right, the oxygen is 16. And the H2O I'm going to do as a group, so it's going to be 18. So the magnesium sulfate part of this is going to boil down to 120. And now you got the pesky dot. And the pesky dot means and. It means plus. All right, and then we've got 18 here for the waters, but there are 7 of them. So you need to multiply the 7 times this. And the grand total we get for that is about 126 approximately. So the molar mass of the entire molecule of MgSO47H2O is going to be about 246. All right, so that just illustrates how you figure out the molar mass of one of these little beasties. Now let's get back to the naming issue. All right, so the thing about the naming is that I don't really think it's that difficult. Here's the deal. You're going to be naming the ionic compound following the same rules that you would for type 1s and type 2s. All right, so for this part of the compound, the magnesium sulfate, the magnesium's out of group 2A, which means that it's a type 1 binary ionic compound, and we don't need a Roman numeral for the charge because magnesium comes out of group 2A. We automatically know its charge is Mg+2. So in terms of the naming on this, we're just going to use its elemental name. So we write magnesium, followed by the name of the polyanion, which hopefully you have memorized at this point. It'll be magnesium sulfate. Now that leaves us with the H2O and the number that we have for this. So the tricky part on the hydrate is that you're going to use Latin prefixes for the H2Os. And the Latin prefixes are those terms mono for 1, di for 2, tri for 3, and so on. All right, and you're going to find this in the chapter on naming, which is in a general chemistry book. Will be in chapter 1 or 2, and I'm not going to go all the way through this in the video. I'll make references back to the list, but it finishes with 10, which is deca for 10. You need to make sure that you've got those memorized. Now, the prefix for 7 is hepta. So I'm going to write that, and then what do we write? Well, to indicate that water is attached to this ionic compound, we write hydrate. So the name of, technically, the chemical name of Epsom salt is magnesium sulfate heptahydrate. Hepta for 7, hydrate to indicate the attachment of the waters. All right, now I want to also do some of the more common hydrates that you're going to see in your classes. So let's look at this one next. It's going to be, and it'll be a transition metal one, so that we've got to deal with the Roman numeral issue. This one also has 7 H2Os. Now, this is an important compound because you'll probably be using it in the permanganate experiments that you do when you get to types of compounds chapter, which is going to be somewhere around chapter 4 in a general chem text. And you'll be doing this reaction. It's a solution redox reaction with permanganate, potassium permanganate solution. This compound, when you look at it, how it comes as a salt, it's going to be a green crystal color to it. And when we go to name it again, we name the front end followed by designations that deal with how many waters we've got, and then the word hydrate at the end. So in this case, since it's a transition metal, we'll start with its elemental name, but we're going to need a Roman numeral to indicate the charge on the iron. Now, these can be tricky because you've got to determine the charge. Well, and how do we do that? Well, the thing that you've got to realize about this is that the way you figure out the charge on the cation with this is by knowing what the anion is. And we've memorized sulfate, so we know that it's SO4 - 2. And when you look at the subscript that's down and right of the iron, well, it's a 1. So that means that the iron and the sulfate have been combined 1 to 1. So the charge on the iron has to be +2. All right, so this is going to be iron 2, and then we have sulfate as the polyanion, and again we have a 7 here, so it's going to be hepta, and then hydrate. All right, now let's do the next one. Will also be a common salt that's used in laboratories. I want to try to stick with things you're going to get exposed to. And let's translate this one backwards. So I'll give you the name of this one. It's going to be copper. And ironically, this is another sulfate. So copper sulfate. And this one is Hexahydrate. All right, so let's do the translation. The copper is copper 2. So I'm going to write that down. I translate my polyanion. It's SO4 minus 2. I inspect my charges, and I do this through charge balance rather than drop charge. If I'm in an advanced class, I must learn charge balance. And I see that the copper plus 2 has the same magnitude in the number as the sulfate anion, albeit opposite in charge, which is an important concept. So these are going to combine together directly. So it's going to be copper sulfate. All right, and then it's pentahydrate, and penta is the Latin term for 5. So this is going to be, all right, put my dot in, and then this is going to be 5H2O. And this comes as a blue crystal. And in the laboratory, you may end up using this substance in the gravimetric determination of a hydrate formula. Like it can be used in lieu of the Epsom salt or along with it, actually. So that's where you may encounter this one in the laboratory. Now, let's do at least one more, and something that's not a sulfate. So one that I like because it's got a really beautiful color is Cobalt 2 Chloride. All right, and this one is Hexahydrate. Hexahydrate. All right, this one is cool because it comes in the bottle as it's a brilliant red crystal. It's really a beautiful crystal. And then when you make a solution of it, it's going to be this, in the diluted form, it's going to be this, light sort of reddish solution. And a key thing here while I'm on the subject is that, remember, the interesting thing is that your transition metal ionic compounds, quite a few of them form colored solutions, like the coppers, the irons, the cobalts, just to name a couple of them, all make colored solutions. And that's something that's actually important to put into your bag of tricks, because the group 1s and group 2 cations, when they form salt solutions, usually are colorless. All right, now let's get back to the subject at hand. So we'll go ahead and translate this. So from the name, all right, our cobalt has a positive +2 charge on it. We understand chloride's coming out of group 7A, so you should automatically know that that's Cl -1. All right, when we look at the charge balance, we see we've got a copper cation that has 2 charges, +2 on it, and the chloride is -1. In order to cancel this charge and get net zero, all right, then what we're going to do is we're going to need 2 chlorides. So this is going to be COCl2. Then we're going to have our dot, and the hydrate this time is hexa, so we need 6 H2Os, all right, and whoops, H2O, and that completes the formula for this. So remember, before we part, that the dot means plus. So if you're calculating a molar mass of these things, find the molar mass of the ionic compound, find the molar mass of the H2O, multiply by whatever this number is, then add the whole thing together. All right, and lastly, transition metal salts, many of them form colored solutions, by contrast to your group 1 and 2 salts that form colorless solutions. And with that, I'm going to sign off.